Okay, so good evening, everybody in India, and good morning to those in the US. I'm very happy to welcome Dr. Narayanan Rangaswamy here to this talk, which is being conducted at both IIIT and IIT as well. So people from IIIT and IIT are joining this. So this talk is going to be on coding theory. So just a brief biography of the speaker. Narayan Rangaswamy completed his PhD from Duke University very recently in May 2020. He was supervised by Professor Henry Pfister and Professor Robert Calderbank. His primary training is in classical information and coding theory and compressed sensing. Prior to this, he completed his master's from Texas A&M University and his bachelor's from Amrita University, Coimbatore, India. During his PhD, he actively learned about quantum computing and quantum error correction, and this is now his primary area of research. He has studied the problem of realizing logical operations on quantum error correcting codes in a fault tolerant manner and produced new insights via a perspective rooted in classical coding theory. His paper on developing conditions for a general stabilizer code to support transversal T gates was accepted as a talk in the esteemed 2020 Quantum Information Processing QIP conference. It was one among the 73 out of 283 submissions that were accepted as talks to QIP 2020. Recently, he has also analyzed a quantum message passing algorithm in the context of classical communications over an optical channel and shown that it appears to be quantum optimal on a example binary linear code. This provides a potential near-term application with a quantum advantage for a special purpose all photonic quantum processor. In general, he is excited about problems in the intersection of classical and quantum information processing and mathematical tools that help address problems of this sort. So that brief introduction. So I would like to thank and welcome Narayanan to this venue, this online venue. So thank you very much, and you can get started.
Thank you very much for the kind introduction, and thank you for inviting me to give this talk. So I hope everyone can see me. So I'm going to talk about quantum error correction. So I'm going to cover some basics. So this is a two-part talk, as you might know. So today I'm mostly covering important basic concepts, and wherever necessary, I'll try to draw a parallel to classical coding, the intuition we have with classical coding theory. And then in the second part of the talk, I hope to show some of the recent developments and some of our own work, and then try to put them in context. So please feel free to interrupt me in between if you have questions, or if you think I should go slower or faster or repeat something, please feel free to interrupt. So with that, let me get started. Yeah, so let me start with some high-level view of quantum error correction and introduce some important basic concepts. So let's say you have some information that you have stored in some qubits. So this notation, is everyone able to see my cursor?
So I think we are able to. So can you just move it a bit?
Yeah. Can you see now?
No. Yes, we can.
Okay. Okay. So yeah, let's say you have some information that you have stored in some qubits. So this notation, I'll in the next few slides, I'll introduce what this notation means. But for now, just think of this as some quantum state that holds your information. Now, what you plan to do is do some operations on the information and then end up in a final state. So this could be, for example, some quantum algorithm. For example, like the famous factoring algorithm proposed by Shor, which provides exponential quantum advantage in factoring large integers. So this could be that kind of, so let's say you take an integer, you encode it into a quantum state, and then you execute Shor's algorithm, and then the answer will be some new quantum state. So this is where all the quantum algorithms happen. And in an ideal world, you would be able to directly execute the algorithm on the information. But the problem is every component of a quantum system is noisy. So if you directly do this path, because your information is just raw information, you won't be able to tell if some noise corrupted your computing. So because of that, we have to take a longer route. So going with the intuition of classical coding, we add some redundancy to the information. And so we encode it into a larger vector space. So this QACC stands for quantum error correcting code. So you take, for example, an NKD code, which means you had k qubits of information here, but you're encoding it into n larger than k qubits. So these are called the physical qubits, and these are called the logical qubits. So in classical coding, we call this the message and this the code word. So that's the parallel. So you first encode, and then after you encode, you can now execute operations on these code qubits. So these are called the physical operations. And so if everything went right, and so these operations are still noisy, but because your code has some redundancy and some non-trivial distance, it can help you correct some of the errors. So you can do some physical operations on your code qubits, and if everything went right and you were able to fix the noise, then you would end up in a state that's hopefully the right encoded state of your actual desired final state. So if that happens, then once you decode your quantum code, then you get back the information that you want. So for this whole thing to work, this diagram should commute. So you should be able to go from here to here by this longer route. Okay, so that's like the higher level view, which is probably intuitive. Now, in order to do this, as you might realize, for every operation that you wanted to do on your information, you have to actually find the right physical operation to do it. So these were k qubit operations, but these are n qubit operations, and there's some encoding procedure here. So for every operation here, you have to first translate it to some physical operation that realizes what operation you wanted. And the added constraint is that you have to make these physical operations fault tolerant, which means you have to guarantee that up to some noise level, the operation that you implemented will succeed with some probability. So this translation is important, and the translation has to be fault tolerant. So this is the problem of fault tolerant quantum computing. Now every aspect of quantum computing or quantum error correction probably fits somewhere in this picture. So for example, experimentalists who do lab operations would care about how best to reduce the physical error rate. So they will try to reduce the physical error rate, and on top of that, we use coding to reduce the error rate. So like in wireless communication, for example, in classical coding, you have some channel error rate, which is your physical error rate, and then you add some coding to it to reduce the error rate even more. So that's the parallel. Now, a question. So there are many questions that are to be answered, but one question that you can keep in the back of your mind for this talk is the following. So clearly, if you're doing some physical operations, and these two have to be code states. So you start with a code state, and your operation should take you to another code state. That means that your operation has to behave well with the code, meaning it has to take code states to code states. There's no point if it takes you outside the code state. So question to keep in mind is what structure for every operation that you want to do in the lab, what is the structure you need in the code such that the operation preserves your code space? So as a high level question, keep this in the back of your mind. We'll often come back to this question in the rest of the two talks. Okay, that's the big picture. Now let's get started with some details. So we need some basic tools. So the first important mathematical tool we need is the Kronecker product. Now, Kronecker product is, you might already be familiar, but let me just go through it quickly. So you have two matrices A and B, and the Kronecker product is defined as follows. So you take every element of A, so A11 through APQ is A is a P by Q matrix. So you take every element of A and multiply it to B. So you replace this single entry with a matrix B multiplied by this term A11. Similarly, you do this for every entry of A. Therefore, you have blown up, so you took a P by Q matrix, but each of the entries was replaced by an R by S matrix times that element. So the whole matrix is PR by QS. So that's the Kronecker product. You can think of this as being analogous to the tensor product. Now, the important property we need of the Kronecker product is that if you take a product of two Kronecker products, then you can take the product term by term and then take the Kronecker product. and this extends to many matrices. So whenever you have a product of two Kronecker products, you can do component-wise product and then take the Kronecker product. So this is a tool that we'll sort of use implicitly or explicitly all the time in quantum computing. Okay. Now, so let's first define what's pure state. So these are like so we saw code states in the big picture. So they are developed from these pure states. So what is a pure state? For a qubit, for a single qubit, a pure state is just a two-dimensional vector. So this is a length 2 vector where the vector is unit vector, so it's normalized. So this notation might be new to you. So this is called the Dirac notation. So this is just quantum notation for the standard basis vectors. So whenever we write ket 0 or ket 1, so ket 0 corresponds to the column vector 1, 0, and ket 1 corresponds to the column vector 0, 1. Now, when you take the Kronecker product, we saw that you replace 1 by 1 times 0, 1. So you get 0, 1, and then 0 times 0, 1 is 0, 0. So this is on 2 qubits. So for a single qubit, you basically have a linear combination of this vector plus this vector. So this is just a length 2 vector with the first component alpha and the second component beta, and it's normalized. When you have more qubits, you just take the Kronecker product of the basis vectors. So, and the key thing to keep in mind is that this binary indexing, so this 0 and 1, gives you the index of the 1 in the resulting basis vector. So you can index the rows as 0, 0, 0, 1, 1, 0, 1, 1. And this 0, 1 tells you that the position of 1, everything else is 0. So you can generalize this to n qubits. So for n qubits, if you have n basis states, so each system is in the ket 0 or ket 1 state, then we just represent this by a binary vector v. So v is this v1, v2 up to vn. It's a binary vector. And that indexes the entry of 1 in this length 2 to the n vector. So that's the complex Hilbert space we work with. And a general pure state is a linear combination of these basis states for all possible v's, because each v is giving you one of the components, and the component is alpha v. And the whole vector has to be normalized, so you have this normalization constraint. So because of this, because all pure states in quantum have to be normalized, and you have to preserve the angles between two vectors, all valid operations in quantum mechanics are unitary operations, meaning that the inverse of the matrix is the same as the Hermitian transpose or the conjugate transpose. So those are pure states, and those are our basic things that we'll work with. So now, so we have quantum state. So we have this pure state, and then we need to somehow have a way of interacting with the state. So how do you? So you can do these unitary operations, but if you have to gather information about the quantum system, you can't really see it. So classically, if we have a code word, if it's a binary vector, we can actually see it. But in a quantum system, the only way of extracting information from it is using a measurement. So what is a measurement? A measurement is defined by Hermitian operators, so P1 through Pt. And these are basically projectors because they square, so the Pi squared is Pi, but projectors are orthogonal to each other. And they have to sum to the identity, meaning you have actually partitioned the whole vector space into these different components. So this is called a projective measurement or a von Neumann measurement. And what happens when you measure? So let's say you have a pure state, phi, and then when you measure, what you get is two things happen. So one thing is you have a post-measurement state. So, okay, actually, so yeah, two things happen. One thing is you learn the index of the projection that occurs, because only one of these projectors get applied. So when you actually measure in a quantum system, you are able to read out which projection occurred. So you have the index I, and if you knew the initial state, then the new state is given by this thing. So ignore the denominator for the moment. Basically what happens is that particular projector corresponding to your measurement result gets applied to the state. So you have Pi times phi, but we saw that every state has to be normalized, and this denominator is exactly that normalizing component. So we have Pi times phi. So Pi is a matrix, this phi is a column vector, and this phi is just the Hermitian transpose of this. So this is called the Dirac notation. I think Dirac wanted this to be a bracket. So this is called so this is like you can think of this is called the bra and this is called the kit. So this is basically a row vector and this is a column vector. So this is yeah, this is just a scalar, and the square of this denominator is the probability that that measurement occurs. So this is coming from the measurement postulate of quantum mechanics, which is also called the Bond rule. Uh, okay, so overall, that's what happens. So when you measure, you learn which projection occurred, and two, you have a post-measurement state, and this measurement occurs with this probability. Now, one thing to keep in mind is in quantum, because all pure states are normalized, no measurement can distinguish between a pure state and a scalar multiple, which is of norm 1. Only norm 1 is valid because it has to be normalized. So these two states are basically the same. So every quantum state is like a ray. So the ray is defined by e to the I theta times state. So this is our primary interaction with the quantum system called a measurement. Okay. The third concept we need is that of the Pauli matrices. So we have these pure states that we defined before. Now let's look at the Pauli matrices. So it's given by these scalar multiples. So the fourth root of unity times any of these things, and the generators are given by these four matrices. This is the identity. This is called the bit flip. So this is like your classical NOT gate. So you take the 0 state, it flips it to the 1 state. If you take the 1 state, it flips it to 0. So this is sort of your classical NOT gate. The phase flip Z is sort of purely quantum. It's new. So on the 0 state, it doesn't do anything. But on the 1 state, it picks up a phase -1. So that's what Z does. And Y is a combination of both X and Z. And you add this I to make it a Hermitian matrix. So we'll see in the next slide how these matrices look like. So this is the key. This group is generated by these four things and fourth roots of unity. And because of xz equals minus zx, you add this I to make y Hermitian. Okay, so those are the single qubit Pauli matrices. What happens when you go to n qubits? Just like we did for pure states, we take Kronecker products of n single qubit Pauli matrices. So here is an example for 3 qubits. So let's say you have 3 qubits in these basis states. So 0, 1, and 1. You have 3 Pauli matrices acting on the individual qubits. So recollect the property of the Kronecker product. Whenever you have a product of Kronecker products, you can do it term by term and then take the Kronecker product. So you apply x to 0, z to 1, and y to 1 to get that. So this is what happens when you have more than one qubit. You just take Kronecker products of the Pauli matrices. So as a term to remember, these states 0 and 1 are also called the computational basis states. In quantum computing, we call them the computational basis. There are also other bases, of course. A vector space can have many bases, but this basis is special. So in linear algebra, we just call this the standard basis. In quantum mechanics, we call this the computational basis. Now, the key property, the reason these Pauli matrices are so nice is because under this particular Hilbert split in a product or the trace in a product, they actually form an orthonormal basis. So to see this, let's go to the next slide where I'll show you the matrices. So here are the 4 basic Pauli matrices. I've ignored the fourth roots of unity. We'll just concentrate on the Hermitian Pauli matrices. So as you can see, every matrix is Hermitian. So this is the flip matrix. This is the bit flip matrix on the NOT gate, and this is the phase flip matrix. And as you can see, the identity has a trace, but X, Z, and Y don't have a trace. So the trace of each of these matrices, each of the non-identity matrices is 0. And when you square a matrix, you can check that its identity. Because it's unitary and Hermitian, it has to square to the identity. And then you can see that the trace in the product of 2 matrices is always 0, because X times Z is Y, and the trace in the product was defined as trace of X times Z, but trace of Y is 0. So similarly, you can check easily that these form an orthonormal basis. Now let's combine the concepts we have introduced. So we introduced pure states, measurements, and polymatrices. So now let's measure Z on these basis states. So what does measuring Z mean? So when we defined the measurement, we said each measurement is defined by projectors. So when you say measure an operator, in this case Z, it always has to be a Hermitian operator. And then the projectors are given by the rank 1 projectors onto its eigenbasis. So the Z matrix, because it's diagonal, the eigenbasis is just the standard basis, which is the 0 state and the 1 state. So the projector is just the outer product, so the rank 1 projector onto the 0 state and 1 state. Now what happens when you measure Z on a state ket Z, where the state is in 0 and 1, the result is deterministic. Because if you apply the rule, you apply this projector onto the state Z, but the projector is just say, let's say the measurement outcome was 0. So if Z was the 0 state, and if you apply P0 times 0, you are applying this ket 0, 0 onto the 0 state. But the inner product between the 0 state with itself is 1. So you get back the 0 state. Whereas if you apply the 1 state, because the 1 state is orthogonal to 0, that measurement can never happen. So that's why with probability 1, you always get the 0 state. So the concept here is that when you measure what's called an observable is just a Hermitian matrix. So when you measure an observable, if the actual underlying state is an eigenvector of the observable, then the outcome is deterministic. It happens with probability 1. Now let's look at the non-trivial case. So let's say you have these what's called the plus minus state. It's defined as a yeah.
So this measurement of Z.
Yeah.
So how did you what is the connection between that and the projectors?
So if you take Z and if you diagonalize it, so it's already diagonal. So the basis vectors are just the 0 state and the 1 state. The connection to the measurement is that the measurement induced by Z, or the measurement of Z, defines 2 projectors. So in the measurement slide, we saw that you can have T projectors. And once you give a Hermitian matrix, the projectors are just given by the rank 1 projectors to its eigenbasis. Is that clear?
Right. Yeah.
Okay. Yeah. So for example, yeah. So whenever you measure an observable, you're just projecting onto one of its eigenbases. Okay. So let's say take this plus minus state, which means you have a superposition of 0 on the 1 state. So again, recollect that the 0 state is just a length 2 vector, where the first entry is 1, the second entry is 0, and this is 0, 1. So when you add these two, you get 1, 1. And when you subtract these two, you get 1, minus 1. So that's these two states. So this is, for example, on the XY plane, this is just a 45-degree rotation of the standard basis. So if you want to visualize like that. Okay, now when you measure Z on this state, what happens is with probability half, the measurement gives you 0. And with probability 1, so with probability half, you get a measurement 1. So the outcome is random. So the outcome is probabilistic. It's not deterministic anymore. Because, for example, when you apply this projector, so you're measuring the same Z operator. So you're taking this one of these projectors, and you can calculate this out of a probability. So you would calculate. You'll apply one of these projectors to the state, and then when you can see that 0 is the inner product between 0 and 0 is 1. So the first component will give you 1 over root 2, but this times the second component is 0 because the 0 and 1 are orthogonal. So Pz times Z is just 1 over root 2 times 0. And then when you take the inner product with 0, you just, this denominator is 1 over root 2, which means the square is the probability, which is half. So basic thing to remember without going through the math is that you can replace this 1 over root 2 by alpha and beta, like we had for an arbitrary state. So if the coefficients were alpha and beta, and if you measure in the 0, 1 basis or the Z basis, then you get a measurement outcome of 0 with probability mod alpha squared, and you get a measurement result 1 with probability mod beta squared. And this is why we actually normalize the vector, because the sum of the probabilities has to be 1. So if you go back to the definition of pure states, so we had alpha 0 and beta 1, and we just saw that when you measure in the z basis, you get the 0 state with probability mod alpha squared, and you get the 1 state with probability mod beta squared. So these amplitudes, if you take the absolute value squared, you get the probabilities for measurement in the z basis. And of course, the probabilities have to add to 1. This is why we have to normalize. So that's what happens. And similarly, the opposite, you can also do the opposite. So if we express the plus minus state in terms of 0 and 1, you can also express the 0, 1 state in terms of plus and minus. And if you measure x there, the same thing happens, because these two states you can check are the eigenvectors of the x matrix. So this 0 state and 1 state were the eigenbases for the z matrix. This plus state and minus state are the eigenvectors for the x matrix. So if you measure x, you are measuring with respect to these projectors. So hopefully that was clear. So measurement is crucial for quantum computing, because that's the way we interact, and the interaction projects the state. So if you had a superposition like this, and if you measured in the basis corresponding to the superposition, then it actually collapses the state. You lose the superposition. And in fact, this is the key thing that we'll use to actually do quantum error correction. It is one of the central results, the very reason that we can even do quantum error correction. So we already saw that the Hermitian polymatrices form an orthonormal basis. Okay, now let's say you have a quantum error correcting code, and then you have these basis states. So the code is a subspace of a larger Hilbert space, and the basis vectors are given by these phi's. Now you want this code to correct a bunch of errors. So let's say the error matrices are given by E sub k. These can be any error matrices. Now Nil and Laflamme gave these necessary and sufficient conditions for there to be a recovery operator that helps you correct these errors. So what does this statement say? So you take a code state phi j, and you apply one of these correctable errors. So you want these errors to be correctable. So you apply one of the errors to that state, and then you take the inner product with a potentially different code state evolving through a different error ek. And he says that so for the first thing is that so this inner product depends on whether the initial states were the same. So if initial states were not the same, this has to be 0, meaning that you should be able to distinguish these two states. So think of, for example, like say for intuition, let's think of the classical repetition code. So let's say, so you have two code words, you have 0, 0, 0, and you have 1, 1, 1. Now let's say a single error occurs. So if you had sent 0, 0, 0, you would get to 1, 0, 0. And if you sent 1, 1, 1, you would get 0, 1, 1. But at the receiver, you just do a majority vote and you're able to correct. The reason is that the Hamming spheres are disjoint. The Hamming spheres centered around 0, 0, 0 and 1, 1, 1 don't interact. And that's the intuition here. So if you start with different code states, then if correctable errors happen, then they should remain, quote unquote, outside their Hamming spheres, which in quantum means that the inner product should be 0, because you can only perfectly distinguish orthogonal states in quantum mechanics. If you have two states that are not orthogonal, there is always a probability of mistaking one state to be the other. So that's the key property. And if you start with the same state, there is this coefficient belonging to a matrix that is Hermitian. So I won't get into how this is exactly proven, because I have to introduce quantum channels and cross operators and things like that. But these are the necessary and sufficient conditions, and the whole theory of quantum error correction is built on top of this. So in general, checking this for a code can be very tedious. I mean, you don't want to really be applying this condition to every basis state, which is a length 2 to the n vector, and checking this. But luckily, we have got a theory for quantum error correction that takes care of this. So overall, roughly, you can make this sort of a statement. So it basically says that once you can correct, so what Nil and Laflamme also showed is that once you can correct a bunch of errors E sub k, you can also correct errors introduced by a channel whose basic errors are some linear combination of these errors. So if you can correct some errors ek, then you can also correct the sum of any linear combination of those errors. And we already know that Pauli matrices form a basis, so any error can be expressed as a sum of Paulis. That's why it is sufficient to correct Pauli errors. Of course, there are some assumptions, but as long as you can correct, say, let's say you can correct Pauli errors on up to t Pauli errors, then you can correct any errors on those t qubits. That's roughly the statement. Of course, there is some independence assumption and some subtleties, which I'm not getting into, but this is crucial because we are able to discretize the error set. You only have to design codes that correct these discrete set of errors called the Pauli errors. And once you can do that, then any linear combination of the Pauli errors you correct is also correctable, or at least there exists a recovery operation that can correct them.
Question?
Yeah.
Can CKL be 0?
Sorry?
Can CKL, those C's, can they be 0?
Yeah, I think the requirement is, yeah, if CKL is 0, I think is the very ideal condition if I'm thinking it right. So if the CKLs are 0, then the code is super protected, I think. But in general, it is not required in the proof. It only has to be a Hermitian matrix.
Okay.
Okay. So this is okay. So the final parallel I want to draw here is that if you think of classical analog computing, there the errors are also a continuous set, just like in quantum, and it's impossible to correct a continuum of errors, and that's why digital computing works, whereas analog computing is very hard to get to work. Whereas actually in quantum, even though you have a continuous set of errors, the measurement allows you to discretize errors in this fashion. You're able to, guarantee that once you correct some discrete set of errors, you can correct linear combinations of them. And this discretization is why quantum computing or quantum error correction can work.
Narayan, there is a question in the chat.
Okay.
So the question is could you please describe the error model?
Yeah, I'm just seeing the chat. So the error model, so that's why I'm saying I have to introduce quantum channels for that. So roughly speaking, a quantum channel is described by a bunch of matrices called cross operators. And then these matrices have to satisfy something called as the completeness criterion. But except for the criterion, the error operators can be anything. So the error model is just a quantum channel described by a bunch of these matrices called cross operators, KRAUS, cross operators. So that's the assumption. So we are not going into like very nitty-gritty details that are hardware dependent. So the error model is just, and so it's a very general error model. So any quantum channel can be expressed using these cross operators, and the statement is just with respect to cross operators. So it's a very general result. Is that clear? I'm also looking at the chat now, so you can. Okay, great. Let me continue. Okay, so we have introduced pure states. We have introduced measurements. We have introduced Pauli operators, and we saw what happens when you measure Pauli operators on some states. And then we looked at the central result of discretization. Now we are slowly getting into building codes. So the key thing, as you might have heard many times in quantum, is that of entanglement. So you say that a state is entangled if the state doesn't split into a Kronecker product. So for example, these are the famous Bell states. And so, yeah, so these Bell states, you can actually check for yourself that there is no way of writing this 2 qubit. So this notation just means 2 qubits. So this is 0 tensor 0 Kronecker 0 plus or minus 1 Kronecker 1, just to be clear. And so you can actually check for yourself that there is no way of expressing this state as a Kronecker product of two single qubit states. Similarly for these states. So these four states are called the Bell states. They are entangled states, and they actually form an orthonormal basis for the dimension 4 complex vector space. Okay, so why is entanglement interesting? So let's say you measure Z on one of the two qubits. Then you can go through the our measurement postulate, and you can verify for yourself that with probability half, the state collapses to this state. So this superposition will collapse to just the 0, 0 state with probability half, and to the 1, 1 state with probability half. But the thing is, you only measured one qubit, but measuring one qubit automatically made the second qubit deterministic. You don't have to measure the second qubit. You already know the answer. And this is the key concept of entanglement. So the superposition gets broken, and one of the two systems becomes fully correlated with the other. And Bell showed using what's called the Bell test that the correlation between the two qubits in such a state is more than what you can have classically. That's called the Bell theorem. But anyway, so entangled states are a crucial thing. So when we build quantum codes, so we saw in the last slide, we looked at these code basis states. So whenever we build non-trivial quantum codes, the code basis states or the code states are going to be entangled states. So we actually store information in entanglement. Now, the other way to describe these states is using as eigenvectors of a bunch of matrices. So in one way, you can actually write down the state, but you can also say that this vector, this length 4 vector, is a +1 eigenvalue +1 eigenvector of these two matrices. So if you have a plus here, it's an eigenvector of x Kronecker x and z Kronecker z. So these two matrices commute. So we saw that x and z anti-commute, but you have two x and z's. So the first thing anti-commute and the second thing also anti-commutes. So overall, this commutes with this. And from linear algebra, we know that when you have commuting matrices, you can simultaneously diagonalize them. And if you simultaneously diagonalize these two matrices, the common +1 eigenvector is given by this phi plus vector. And if you have a minus sign here, then it's the phi minus vector. And similarly, you can take these two matrices. If you have plus here, you get the psi plus vector. And if you have minus here, you have the psi minus vector. So what's important to note here is that instead of describing, instead of giving you the state itself, if I had just told you that the state I have is the +1 eigenvector of these two matrices, I have already uniquely identified the state. And these sets of commuting polymatrices are called stabilizers. The word stabilize is just used to mean that it fixes the state. So you do XX on the state. So X flips this qubit and this qubit. So this becomes 1, 1. But it flips this qubit and this qubit, so it becomes 0, 0. So overall, you get the same state in the plus case. But for the minus case, you get a minus out, which is why you have a minus here. So you can see that this XX fixes the state. And for fixing, we call it as stabilizing in quantum. So commuting operators are stabilizers. And stabilizers is what we'll use to define quantum codes. OK. Let's start with a basic code just to draw parallels to classical computing. So this is sort of like a repetition code, but it's not exactly. So you have, let's say, one logical qubit. So you have a single qubit, the basis states being 0 and 1, and you're encoding into 3 physical qubits. So the encoding is defined only for the basis states, and because quantum theory is linear and the encoding is linear, by linearity, you can apply the encoding to each state. So the superposition will get encoded into these two. So 0 is encoded into 3 zeros and 1 is encoded into 3 ones. So for the basis states, it does look like a repetition code. But if you have a general linear combination here, the encoding of it is not 3 copies of that. So if, for example, you can check that the 0 plus 1 state doesn't go to 3 plus states. So this is the plus state. So this is not a repetition code. And in fact, there is this theorem called the no cloning theorem, which is a no-go theorem, which says that you cannot clone arbitrary quantum states. You can clone these sort of basis states, though they are special cases, but that's not of much use. And in fact, you cannot clone arbitrary quantum states. So simple repetition that works in classical coding does not exactly work in quantum coding. Okay, now let's look at this code. So let's we looked at entangled. So for example, whenever alpha and beta are both non-zero, you can see that these two states are entangled. So this psi bar is an entangled state whenever alpha and beta are both non-zero. And so we are encoding into an entangled state. Now, just like we saw in the previous slide, we can describe these states, this code state, using stabilizers. So in this case, the two generators for the stabilizer group is Z Kronecker Z Kronecker I and I Kronecker Z Kronecker Z. So what this is basically doing is, so let's say we apply the ZZI to this basis states. So we saw that Z on 0 doesn't do anything. So ZZ on this doesn't do anything. Z on 1 picks up a -1, but you're doing two Z's. So Z on the first one picks up a -1 and the second one also picks up a -1. So overall, you get only a +1. Therefore, ZZI fixes the state. So this is a +1 eigenvector of ZZI. And similarly, you can also check this for the second thing. What this is basically doing is that it's checking that the adjacent bits have the same value. That's how we classically check a repetition code. So if you had a classical repetition code, the parity check matrix basically checks that any two adjacent matrices, any two adjacent bits are the same. And this is the quantum way of doing it. So you measure this stabilizer, and the measurement result has to be +1. So the eigenvalue of the matrix or the measurement result has to be +1. That means you're in the right code state. If you get a -1, then it means your code state has been corrupted. So that's the parallel to classical coding. Now the additional thing you want to note is, so let me for a second go to the previous slide. So here we saw that once you specify these two 2-qubit matrices, then once you say it's a +1 eigenvector common to both of them, I said we uniquely define this 2-qubit state. Whereas here we have a 3-qubit state, but here we only gave two stabilizers, generators, which means there is an additional degree of freedom. So these two stabilizers don't uniquely define one state, because both the 0, 0, 0 and the 1, 1, 1 are fixed by these two vectors. And that's why you're able to encode 1 qubit, because if you only had a unique state that is fixed by the stabilizer, you can't encode any information. Whereas because you have some redundancy left, so there is some space to store some information. So when you specify two stabilizers on a 3-qubit system, there is 1 qubit of information that you can store. And so if you want to uniquely define the 0, 0, 0 state, in addition to these two generators, you have to add another generator. Let's say Z on the first qubit, because Z on 0 is 0. So if you want to uniquely define this state, you have to give 3 generators, which is these two plus this. And similarly for this state, you need these two generators plus this. So minus, because Z on 1 picks up a -1. So hopefully that was clear. So if you have an n qubit system, if you define a stabilizer group with n elements, n generators, then you're uniquely defining that state. Whereas if you have lesser number of stabilizer generators, then it's not completely determined. So there is some freedom, and that freedom is where you use to store information. This is like parity check matrices. So the stabilizer matrix is just like parity checks. So classical parity check says that every code word X should satisfy HX transpose is 0. So the syndrome is 0. Here we are saying that the measurement of stabilizers should give you a +1 result. So that's the parallel. So stabilizer codes like here are just like classical parity check codes. Okay. So here, yeah, so I want to sort of crystallize the idea here. So whenever you have a state psi bar or some state psi, and you're acting by a unitary U, let's say you know one stabilizer for the state. So introducing the ZZI fixes the state, so you can freely introduce this. And once you introduce this, because U is a unitary, you can also introduce U dagger U, because this is just identity. And then you combine this. Now, if you compare this with the state you started with, you see that this operator fixes this state. So this U psi is a +1 eigenstate of this operator. And so the other way to say that is that this operator is in the stabilizer for this state. So usually we work only with poly stabilizers. So in general, this operator need not be a poly matrix. But just intuitively, I'm saying if you take the stabilizer notion in a general sense, this operator does fix this state. And so instead of evolving states through operators, so instead of evolving psi by u, you can actually just take the stabilizer and evolve it by this conjugation by u. So these two are equivalent. And this is called a stabilizer formalism, and it's very super useful and makes a lot of things easier, because keeping tracking of this length 2 to the n states is just super hard, whereas keeping track of these stabilizers, in some cases, it's much easier. Okay, now let's say what happens when errors act on your state. So if no error occurs, so if the identity occurs, so if no error occurs, then the stabilizer for the new state is just the original stabilizer, and your syndrome is +1 +1. So the eigenvalue of both operators is +1. Whereas let's say you have the poly x error acting on the first qubit, means this becomes 1 0 0 and this becomes 0 1 1. Now if you measure the two stabilizers, so ZZI, because you have a 1 0 0, you pick up a -1, and because you have a 0 1 1, and there's only one Z here acting on 1, you get a -1. So this eigenvalue becomes -1, whereas the second eigenvalue is still +1. So if you measure these two operators on this state, then you get a result -1 and +1, and you can infer that something equivalent to the X error happened on the first qubit. And let's go to the next. So similarly, you can check for X errors on the other qubits. And so you have 4 possible syndromes. They are all unique to the 4 possible error patterns. So this code can correct any single X error. And the thing to note going back to this conjugation is the following. So one way to check the syndrome is to actually take the error, act on the state. But like here, you started with a stabilizer, and this U was say X on the first qubit. So you can just conjugate this operator by X on the first qubit. And we know X and Z anti-commute. And that's why ZZI becomes -ZZI. So in effect, this syndrome value is just given by whether the error commutes, so the poly error commutes with your stabilizer or no. So that's how you detect syndromes. So you detect syndromes by measuring stabilizers, and if the error commutes, the syndrome will be +1 for that stabilizer. If the error anti-commutes, you get a -1. So because X errors anti-commute with at least one of the two, you can correct X errors, but Z commutes with Z. So if you have Z errors acting on the state, so Z acting on this state, then Z commutes with both of your stabilizers, and so you will never see the error. You will never detect the error. So that's why this is like a classical code. So because it can only correct bit flip errors. Now, Peter Shor came up with this idea of correcting Z errors. So for Z errors, instead of encoding into 0 0 0 and 1 1 1, you can just encode into plus 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 and minus minus minus. And by similar analysis, you can check that this code can correct a single Z error, but it can't correct an X error. And therefore, to correct both X and Z, Shor showed that you can just concatenate the two codes. So you first encode your single qubit into this state, and then you take each qubit here and encode it into this code. So you have a concatenated code, and then he showed that any single X or Z error can be corrected. And by the discretization of errors principle, any linear combination of X and Z, or so any arbitrary error on a single qubit can be corrected. So hopefully that was clear. So what are the errors doing? So there's a mathematical way of seeing what the errors is doing. So one is the syndrome, but basically you can define a general stabilizer, which is a function of this eigenvalue. So these two values can. Yeah.
Okay, so this is Lakshmi Prasad. I'm from IIT Hyderabad.
Sure.
Can you maybe tell us a little bit more about the syndrome? What does syndrome mean here?
Yeah. So maybe I'll draw a parallel to classical. So let's say, so just think of this as the classical repetition code for a moment. So think of 0 0 0 and 1 1 1 as being separate. So not a quantum state, just two classical code words. If a single error occurred on the first bit, then when you apply the parity check matrix and compute the syndrome, you will get the syndrome for a single flip occurring on the first bit. Analogous to that, if a single X error happens on the first qubit, because you have a superposition and the operation is linear, it acts on both states. So this becomes ket 100 plus ket 011. And then you measure this your stabilizer. So classically, you would apply the parity check matrix onto the received vector. Here you can't see this received vector because, I mean, it's a quantum system. You can't really see it. The only way is to measure it. So you measure your two stabilizers, and when you measure ZZI, let's say, so you think of this as 100. If you apply ZZI on 100, you see that Z on the 1 picks up a -1, and Z on the 0 picks up a 1, and then you have identity. So basically, now the eigenvalue becomes -1. And similarly for this state also, you have 0, 1, 1. If you apply ZZI, Z on the first 0 doesn't do anything. Z on the 1 picks up a -1, and the identity on the third qubit doesn't do anything. So for both states, you get a -1 eigenvalue, and that is what you will read out. So the actual lab measurement of these two operators will give you the result -1 and +1. And so that's your syndrome. And then you can have this sort of syndrome lookup table that maps this syndrome to the X error. So because this is the simplest error that can cause this syndrome. Is that clear?
Yeah. So what happens when the state is entangled?
The state is already entangled. So because quantum theory is linear, so whenever alpha and beta are both non-zero, this state is entangled. You cannot express it as a canonical product of single qubit states.
Okay. So irrespective of the value of alpha and beta, the syndrome remains the same.
Exactly. That's the point. So if you measured, good question actually. So we are doing measurement in a clever way that is not so. Remember that alpha and beta is your logical information that you have encoded, because if we go back to the encoding, we took this logical, so your logical state is basically defined by alpha and beta. And so in the code state, alpha and beta is what is carrying your information. But we didn't try to learn alpha and beta. If we tried to learn alpha and beta, then we would collapse the state. So we are measuring these operators because irrespective of alpha beta, these should fix the state. And so you're doing measurement in a way that the post-measurement state, which we saw can collapse, doesn't happen because you're not trying to learn alpha and beta. You're just making sure that your state is in the right subspace. The subspace is your code. Is that clear?
Yeah, thank you. Thank you.
Yeah. Okay. Right. So what is happening? So let's look at a high level. What are these errors doing? So you can define a general stabilizer as a function of two numbers which are plus or minus 1. So these numbers can take plus or minus 1, and these are the 4 possible stabilizers that you can get from these 4 possible errors. One of the error being the identity. So you can just combine these 4 things into one sort of function and define the stabilizer. And you can define for each epsilon1, epsilon2, you get a stabilizer code with almost the same properties as this code. So the code defined by these 2 operators is equivalent to a code defined by these 2 or these 2 or these 2. They have the same distance, they have the same properties, essentially. The projector onto this subspace for a particular epsilon1, epsilon2, you can check that it is given by this, simply because projecting onto the +1 or +1 eigenspace of a Hermitian polymatrix is given by this operator. So we saw this in the measurement slide, measuring the poly operator slide. And using that property, because you have 2 generators and they commute, so the projection can happen in any order, but the product of the projectors onto the epsilon1 eigenspace of this operator and the epsilon2 eigenspace of this operator, that's the code projector. So this defines the projection onto the subspace. And the resolution of the identity is that these 4 projectors corresponding to the 4 possible values of epsilon1, epsilon2, sum to the identity. So you've basically partitioned the whole Hilbert space into 4 things, and errors basically move you between one of the 4 things. So any error, any poly error takes you to one of these 4 things. So we saw this single qubit X error, but you can also, for example, try 2 qubit X errors, and you can only still get these 4 possible syndromes. So any poly error just moves you in the resolution, and measurement tells you which part of the resolution you are in, and then you apply a correction operator to go back to the right part of the resolution you want to be. So here, the right part of the resolution was both being +1, and whenever errors happened and you detected some non-trivial syndrome, so for example, let's say the X2 error happened, you get -1, -1. Once you see this, you apply the X2 operator, and you fix these minus signs and go back to this part of the resolution. They have 4 parts, and errors move you around these parts, and error correction takes you back to the right part. This is just classically syndrome. So you have, let's say you have a binary linear code. For each non-trivial syndrome, you can sort of define a coset of the code. And you know that the union of all the cosets will be the full binary vector space. So similarly here, it's exactly this projection intuition. So poly errors just move information. Okay, so we have introduced entangled states. We have introduced the concept of a stabilizer, a syndrome, and error correction. Now, one final piece we need to complete this picture is encoding. So let's look at how we will encode into this code. So define the Hadamard and control knot operation. So Hadamard you might be familiar with. So it takes the 0 state to the plus state. So the 1, 0 vector to the 1, 1 vector, which is the first column, and the 0, 1 vector to the 1, -1 vector. And an equivalent way of saying that is that it takes the z basis to the x basis, because this plus and minus state are the eigenvectors of the x operator. So H takes z to x or x to z. So that's what Hadamard does. And we use the Hadamard transform in classical coding as well. Okay, the control NOT gate is similar to the XOR gate from classical computing, but except that you make it reversible. So you retain one of the inputs. So let's say you have 2 inputs in their binary. So this is a computational basis state. So it flips the second qubit if the first qubit is 1. So it does the XOR, but it also retains one of the inputs so that the operation is reversible. So this is like reversible classical computing. We already defined the XFlip code. So we defined this code, which we showed that every single X error can be corrected. And similarly, you can do the ZFlip code, which is what Shaw did, Peter Shaw did. So replace just Z's by X's, and then you replace zeros by pluses and ones by minuses. This code can correct single Z error. And so encoding into the first code that we introduced is given by this circuit. So this is a unitary circuit, and this is the notation for the control NOT operation. So this says that if this qubit is 0, don't do anything here. If this qubit is 1, flip this. So let's try to encode. So let's try to encode just the basis state. So the 0 basis state maps to the 0, 0, 0 state. Let's check that. So if this psi was just 0, let's say alpha equals 1 and beta equals 0. So if you have 0 here, then C0 says don't do anything to the second qubit, and you already initialize these to 0. So you get 0 becomes 0, 0, and this also becomes 0, 0. So you basically get 0, 0, 0 here, which is the first part. And for the second part, if you have a 1 here, so control NOT says flip the second qubit. So 1 goes to 1, 1, and 1 goes to 1, 1. So you get to 1, 1, 1. So that's the encoding of the 2 basis states. And because this operation is linear, any linear combination of the input states will work. The only change for the ZFlip code is that you have to change 0 to plus, but that's what the Hadamard does. So you map, after you do the encoding into the first code, you just apply 3 Hadamards and you have the second code. So this is a unitary encoding circuit, and it encodes 1 qubit into 3 qubits. Hopefully that's clear. So the last piece of concept I want to introduce before we generalize, maybe I don't have time today to generalize, but so the last piece of information is So far we have seen this mapping between states and operators, right? So we had a state and we said you can equivalently represent it as the unique +1 eigenvector of a bunch of commuting matrices. Now for some special states, those commuting matrices are poly matrices, but for other states, they need not be polys. But let's not worry about the others. Let's look at only those that are fixed by polys. Now, instead of thinking as a qubit as this length 2 normalized vector, you can equivalently think of it as just a pair of bases, x and z. So this can be very abstract, but let's see what this means. So you can think of it as a pair of bases, x and z, that anti-commute. So why is this true? So let's try to get some intuition. So we said that any single qubit state can be written as alpha 0 plus beta 1. Now equivalently, you can just write this as a linear combination of polys, because any unitary matrix can be written as a poly matrix, and any state like this can be prepared by applying some unitary onto the 0 state. And so we are just expressing that unitary here. So you denote a single qubit unitary as a linear combination of polys, and there exists some numbers that can make this work for any alpha and beta. Now, if you apply a unitary to the state psi, so you're applying a unitary here, but u is unitary. So again, we are free to introduce a u dagger u, just this identity. And now you just combine the u with 0. So irrespective of alpha and beta, this is a fixed state. So that's the first thing to note. So u0, you already know what u0 is. Once you know what u is, you know what unitary you're implementing. So u0 is deterministic. The only thing that you don't know is the result of this conjugation. And term by term, you just have to know how u acts on x, what ux u dagger is, and what uz u dagger is. Because y is x times z, these two operations already tell you what happens here. So all you need to know is what happens when a unitary acts on x and a unitary acts on z. That's why you can think of a qubit as just a pair of bases x and z. Every time you do an operation, all you have to do is evolve x and z through that operation. By evolve, I mean conjugate. So if you have x and z, and if you did u, the new thing is ux u dagger and uz u dagger. That's all you need to know. Therefore, if you had k qubits in hand, a useful way of thinking about it is as k pairs of x and z. So x and z on the same qubit I anti-commute. That's how x and z are defined. But x and z on different qubits must commute, because two qubits don't talk to each other. So thinking of this way is very useful. Now let's apply this concept here. So we saw this encoding matrix, and let's say you want to do, so this is a unitary operation. So think of this as, you had some initial state, and this is a unitary. Let's say you wanted, now remember in the lab, you only have access to psi bar. You don't have access to psi. In fact, so one thing I should mention here is in classical coding, we have this concept of systematic encoding, where the messages are still retained in the code word, and then you have n minus k redundant bits. But in quantum, there is no systematic encoding. So once you encode, your information is sort of present in the entanglement. You can't really see it. And so if you want to do any operation on your information, you have to operate directly on this state in the lab, which is this 3-qubit state. So if, let's say you wanted to do an X operation on this psi. So how do you do it in the lab? So you have X here, and you want to know what is the equivalent operation here that applies X here. You can apply this concept of evolution. So X here, and then you have a unitary here. So the result will just be this unitary X unitary dagger. And you can actually work out that X here, if you evolve it through the C naughts by this conjugation, you get XXX. So this is called a logical poly operation, because this X bar or XXX implements X on this qubit, and you can check it by the encoding. And similarly, Z on this qubit, if you evolve through the C naughts, it doesn't change. So you just have Z on the first qubit. And so these two operations define your logical polys. But in fact, instead of thinking of them of one operation, you can think of them as coset. So the stabilizer is a group, and you know applying a stabilizer to the state doesn't change the state. Therefore, whenever you want to apply XXX here, you can also freely apply XXX times any stabilizer. It doesn't make any difference. Therefore, really speaking, the logical polys are actually cosets of the stabilizer in the poly group. So to summarize what I've said here is that you can define a code in 3 ways. So the first way we saw is by defining the basis states. And then the second way we saw the encoding circuit. And the third way is to define these logical polys. And when I say logical polys, I really mean these cosets. So one thing you could think about today is if you wanted to do the Hadamard on this operation, on this logical qubit psi, what is the right 3-qubit operation that does the Hadamard? And if you think about it, you will see that thinking about it this way is not always, I mean, it is conceptually right, but every time evolving this through this conjugation can be quite tedious. So this is something you can think about today. Okay, so let me summarize this first part. We first saw that pure states are unit vectors and all operations have to be unitary. Then we saw that the poly matrices form an orthonormal basis. And so any error can be expressed as a linear combination of polys. And so it is sufficient to correct poly errors. Now, and then measurement of a poly projects onto an eigenvector that gives you an eigenvalue as well to know which part of the Hilbert space you are in. Then we saw entangled states, and we saw that they can equivalently define by commuting polys from stabilizers. Once you define stabilizer, we define a code as the +1 eigenspace of everything in the stabilizer. And we saw that this subspace in general has some space where you can encode information. But for an n-qubit state, if you give n generators and they all commute, then it uniquely defines the state. There is no space left. Once you have a stabilizer code, the way of knowing what error happened is to measure the syndrome. And then once you measure, the way you decode is to map to the likely poly error. So there's 3 different ways to define a code using the basis states or the encoding circuit or the logical polys. The most useful thing to remember is the logical polys, and that's what we'll see the remaining of the talk. Finally, once you have defined a code, in order to do encoded computation, you need to define logical operators. So what are the lab operations that realize a target operation on your encoded information? Those are called logical operators. Okay, so that completes. So I tried to introduce quantum error correction and through an example, and we introduced a bunch of concepts. The remainder of this part was actually to generalize this to arbitrary stabilizer codes, but I'm probably not on time. So I could stop here and maybe I can continue tomorrow. So
thank you so much.
Yeah.
So if there are any questions, then we can take them now.
Yeah. So actually, I think so. Given the time it took, I may not be able to complete the full talk even tomorrow. So I'll try to maybe crystallize the remainder, or I'm also happy to share these whole slides with anyone who's interested.
Sure. Okay, so maybe we'll continue tomorrow then. So I guess there are no questions as of now.
Yeah. Thank you.
Okay, so thank you so much. So tomorrow we gather at 6:30 p.m. Indian time. Right. Thanks a lot.
Thank you.